talking about the Higgs particle in CERN, of course. Peter Higgs predicted the Higgs-boson already in 1964. Then in 2012, this boson was discovered in the CERN Large Hadron Collider at CERN for the very first time that it was seen, so to say. Scientists describe this like landing on the moon. It's just so big, this event, they experienced it. What can we learn from them? They can be transformed into dark matter particles, so maybe this explains something about the dark side of our universe. These are questions I asked to Tristan, and he will address them in a few moments. At the same time, while the collider is producing Higgs particles, scientists, and Tristan du Pree is certainly one of them, are dreaming of discovering new particles and new unknown forces. That's of course the dream of every higher energy physicist. Well, perhaps a brand new future circular collider, which is much bigger than the current one, is able to expose these new particles and forces. That's a very, very exciting development. Tristan will, of course, talk about this new future collider, where it will come, when, and things like that. And I fired all these questions at Tristan du Pree. He is a professor at this university in high energy physics, and he is also a particle physicist at NIKHEF in Amsterdam, which you probably know. Can we have a big hand for Tristan du Pree? Yeah, go ahead.
Okay, thank you very much for this very nice introduction, Peter. It's a pleasure for me to be here in this very nice room here from Studium Generale in Twente. So yeah, as was already alluded to in the introduction, I will speak about the prediction of the Higgs boson, the discovery of the Higgs boson, also what we're going to do in the future. But let me first start with a riddle. Do you know what this is? I don't see many people here in the audience who also follow my lecture, so anybody, any clue? Yeah, go ahead. Good guess. I mean, at first sight, you might more think like this is some kind of medieval or medical apparatus, but actually, this was the first cyclotron. It was made in the year 1931, so almost 1 century ago. As you can see, it's 4 inches big, so 11 centimeters. And what you do there, you have a charged particle that you can accelerate. If you put a potential difference between this, you can accelerate it, and with a magnet you can turn it around, and then you can accelerate it again and turn it around, accelerate it and turn it around, until it doesn't fit anymore. And if you do this 80,000 times, you get an energy of 80 keV, 80,000 electron volts. So that was the state of the art in 1931. Now, let's fast forward to 2025. So this is our current best accelerator. Here you can see the Lake of Geneva. Here you can see the Alps on the background. Here you can see the CERN site. Here you can see the village that I was recently living. And this is the Large Hadron Collider. It is, if you take the simple equations from high school, so the centripetal force mv squared over r, and the Lorentz force qv times b, then you can see that we get an energy which is much, much bigger than we had before, namely 30.6 TeV. So tera electron volt, a million billion electron volts. So we have a circumference here of 27 kilometers. So of course that is much bigger, but we also make much bigger magnets, which we actually do at the University of Twente. And that's why the developments of Twente are very important for what we do at CERN. So these magnets are so important that they even let me talk about them at NPO2 with Diederik Jekyll, actually an alumnus of Twente. I was standing here in front of one of these accelerating magnets, and to show what an expert I was saying even E equals mc squared, so you also really know what I'm talking about. And why is this formula so important? Because if we have high energy, if we have high collision energy, we can make particles with a large mass, very massive particles. So E equals mc squared is very important for us, because if we have very strong magnets, we can reach high energies, so we can create new massive particles. Now, for this, it's very important to have magnets which are as good as possible, and that's why we have a ring of 27 kilometers all filled with magnets that are only 2 Kelvin temperature, minus 271 degrees Celsius. So these magnets are made of niobium titanium, and they produce a field of 8 Tesla. And because we make these very strong magnets, we can reach this very high collision energy. Now, I was working here at the LHCb experiment next to the airport of Geneva for 4 years. After that, I went to the CMS experiment next to the Jura Mountains, where I worked on the discovery of the Higgs-boson. And then I went to the Atlas experiment, where I'm currently working on the main CERN site. So I made almost one full circle in 10 years, but the protons actually make 10,000 circles per second. That's how fast they go, because they go almost the speed of light. Now, a little bit about myself. I'm originally from Rotterdam, then I studied theoretical physics in Utrecht. Actually, this week Gerard het Hoofd got the Breakthrough Award, and it reminded me of that I followed his lectures on string theory over there. Then I got my PhD in Amsterdam on the VU, where I studied antimatter. I went abroad for a while, so I was also living at CERN, and also in the city of François Englert, who actually also predicted the Higgs mechanism. And since 2017, I came back to the Netherlands at NIKHEF, and since a few years, I'm also a professor at the University of Twente. Now, to explain a bit how we do this, so this is our camera. Of course, we don't make a real picture of the event, but we have so many sensors that we can reconstruct what happened in a collision. So it's kind of like a cylindrical shaped onion. This is called the compact muon solenoid. It's compact because it's only 25 by 15 meters. Our other detector is slightly bigger. You can see here a person for scale. And here in the heart of the detector, we have semiconductor trackers that can reconstruct the event. Here we have calorimeters that can measure the energy. And here we have a very strong magnet, again a magnet, that is so strong that we can reconstruct the particles very well. So a few numbers about this. The magnetic field that we have here in the detector is 4 Tesla, but it's a very big magnet. The detector is 30 by 15 meters, and the overall weight is 14,000 ton. So very heavy, and that's because all this red stuff you see here is metal, and that's to conduct the magnetic field that we produce here in the solenoid. And altogether we have millions and millions of readout channels in order to make a very precise reconstruction of the collision event. So what does the collision event look like? Here you can see a picture of a colleague of mine who was working on the detector construction about 15 years ago at Imperial College in London. What we are doing is we place detectors here, semiconductor detectors, over which there's a high voltage. When there is a charged particle passing by, it creates hits in the detectors. And from these hits, we can again estimate the curved tracks. From these curved tracks, we can, if we know the magnetic field, we can reconstruct what the energy of the particle was, and thereby we can see what mass the particle had that was produced here in the collision. And then we can see if we maybe discover a new particle. So in principle, this is very simple, but in practice, this is quite a mess, because we want to have many collisions. So we interact the beams, the beams collide with each other 40 million times per second, and every time we collide them, we produce multiple interactions, maybe up to 100. So every collision, we have a needle in a haystack we have to look for, but we also have 40 million haystacks each second. So we have to find one needle in 40 million haystacks per second, because we have like 1 billion collisions in order to find one Higgs boson. Okay, so how do we do that? We don't just reconstruct particles, we can also identify them. So for example, if you have a photon, we all know the photon, the messenger, the light particle that's also the messenger of the electromagnetic force. The photon goes straight through, it is not charged, it's not deflected by a magnetic field, and it deposits energy here in a calorimeter. But for example, an electron is charged and it gets bent in a magnetic field, Lorentz force. So in this way you can see that this is an electron because it's bent, and this is a photon because it's not bent. And for example, there's also muons which fly further, which are also bent, but they fly further. So in that way, we cannot just reconstruct them, but also identify the kind of particles that were produced. So I was already mentioning magnetic fields. They are very important for us. So of course at school you also learned about the Lorentz law. A friend of mine, actually my former office mate, Ivo van Vulpen from Leiden, he made this kind of muurformules. So it's kind of like gravity for nerds. So he put the famous equations that originated from Leiden. He also lives in Leiden. He put them on the walls to illustrate them and give a brief explanation. So it's very nice. And also the Lorentz law came from Leiden because Lorentz was professor there. And this right-hand rule is very important for us because for the accelerators, the right-hand rule is related to the collision energy, and in the detectors we use it to reconstruct it. Actually, we don't say right-hand rule. To our students, I say it's the CERN gang sign. CERN gang sign, very important for us. Now, what do we do then? So suppose we have two muons and we measure their energy, and we can then reconstruct their mass. You can then see if you put them all in a histogram, so you measure it, you all say like, okay, I measure energy 1, I measure energy 10, I measure energy 100, I put them all in a histogram. You can see small bumps, and these bumps correspond to particles that decay to, for example, a pair of muons. So here we can, for example, have the phi meson, which is 1 billion electron volt. You can see here a little peak, which was a phi meson decaying to 2 muons. Here you can see the J-side particle, which also likes to decay to a pair of muons. You can see it here at a peak of 3 GeV. So in this way we can see particles and check that the detector is working properly. Here you can see the Z-boson, which has a mass of 90 GeV, so 90 billion electron volts. Now, these particles are all well known already since the 50s and 60s, 70s. I think this was just the beginning of the 80s. So these are well known, but in this way we can also check that our detector is working and that we indeed see the particles that we want to see and that we want to use to discover new particles. Now, how do we reconstruct it? In the old days, this was actually done by eye, and it was actually very nice. So if you make a cloud chamber, so this is a vapor of alcohol, so it's basically like a fog. Then when charged particles pass by, this fog can condensate, just like a way that the airplanes in the air that they make condensation trails. The charged particles in a cloud can also make this condensation trail. So in this way you can really see with your own eyes, you can actually see charged particles. So this is the way you can see it at exhibitions. I also like to make it in my lectures every year. But the way it was done until actually not so long ago, this was from the 1970s at CERN, the Gargamel bubble chamber. You can see here, which it looks more like a Jules Verne kind of Suske and Wiske Professor Barnabas apparatus. You can see here the place where the vapor was, and here you can see the piston, so the zuiver. So every minute or so, this piston was put in order to put again the pressure correctly, and then a new picture was made. This actually worked very well. So at the time, people were just sitting in chambers where these pictures were projected and checking like, are there actually some new tracks in there that maybe could indicate new particles? And in that way also new particles were discovered. For example, the neutral current was discovered from neutrinos that came in. You can see here all kinds of particles being produced, kaons, pions. And in this way, actually, you could do very interesting measurements. However, it's very slow. Yeah, so by eye you can maybe analyze 1 per minute. So if you want to find a process that's very rare, this will not work at some point. And of course, it's also very labor intensive. Now we'd like to have like 1 billion collisions per second. We have to do it differently. And that's why we automatized everything. And that's why we read out everything digitally and make algorithms in order to process the data. And how much data do we process? Well, if you would record everything, you should think about like 1 terabyte per second, because our detector is millions of channels, so you typically have 1 megabyte per collision, and you have 1 billion collisions per second, so you can do the math. You would need a lot of Dropbox accounts to catch up with this. Of course, we cannot do that, so in the end we only record like 100 collisions per second. Okay, so 100 we record and 1 out of 1 billion, and the rest we throw away. So we have to think beforehand very carefully which ones we want to keep and which ones we throw away, because when we throw them away, they're gone forever. So how does an event look like, for example, one that is interesting that we want to record? Well, for example, if you have an electron and an anti-electron, that we call a positron, if you combine them and you find an invariant mass of 90 GeV, then this might be a Z-boson. If you have a muon and you have an anti-muon, and you again estimate the invariant mass of that pair, it might be also a Z-boson decaying to a mu-mu. And we know that a Higgs sometimes likes to decay to a Z and a Z. So when we see an energetic muon or an energetic electron, we say like, that's interesting, that one we should record and put to storage to analyze later. Similarly, the Higgs boson also likes to decay sometimes to photons. So, for example, a photon is not charged, it just flies and creates some energy deposit here and an energy deposit there. You see not much action otherwise in the detector. But if you see an energetic photon, you know like, that is cool, we should store it and maybe analyze this later for discovery. Now then we make a lot of simulations. So here you can see PhD theses of students from NIKHEF who were doing this research before the discovery of the Higgs boson. So they simulated the detector. They also simulated the distributions of the backgrounds in blue and the Higgs signals in red to see like, can we find a little bump here on the data that might indicate a new particle. So here, for example, a Higgs-2 photons of a mass of 130 GeV. Here a Higgs-2 Z-bosons with about 150 GeV, or here a very heavy Higgs boson. In that way we know what we can expect from our detector, and if we can do a discovery, and if we can maybe improve our analysis to do this discovery. Now then, what did we see? So everywhere in the world at 4 July 2012 we were ready to look at the data. We nerds like to call this now Higgs Dependence Day. Of course this was Independence Day, but for us it's now forever Higgs Dependence Day. So here you could see some of my colleagues at CERN. You can see at the time the spokesperson of Atlas, but now the Director General of CERN, and the Director General of CERN at the time. We also had a big conference at the time in Australia, so some of my friends were actually sitting on the other side of the Earth, but they were still looking at CERN. You can see here Fabiola's red shirt they were looking at. And in Amsterdam, at NIKHEF, you could also see us looking at the screen, the director at the time of NIKHEF and the current director sitting at the tip of his chair. I always like that. And here you see a bunch of students
actually Escher here, he studied in Delft, and this student, Fabian Janssen at the time, he actually also came from Twente. He was a student from Twente. So the whole world was looking what we were going to show them, and what we were seeing was this. So if you look at the invariant mass here of 2 photons, you can see a smooth distribution, so not much exciting. It's like, okay, looks like just background, but you slowly see here some data peaking above the background, which might indicate an excess, which might be a significant amount of data that indicates a new particle. So this is the decay to 2 photons, but we also looked, for example, of the decay to 2 Z-bosons. So here you see less data, but you also see less background. And again, you see slowly some data popping up above the background. So here you could see it was at 120, 125 GeV, and also here you can see around 125 GeV again, some excess of data above the background. So we saw this one. Well, that might be very well some discovery, right? But of course we don't just do that by eye. We do statistics. Of course, if you throw a head and coin, you don't always throw 100 times, 50 times head and 50 times tail, right? Sometimes you do more, sometimes you do less. So you want to know how significant an excess is. But if we calculated it, we saw that the excess around 125 GeV actually corresponded to a chance of 1 in a million that this was a statistical fluctuation. Okay, so it might be a statistical fluctuation, but really with a chance of only 1 in a million. So that is what we call a 5 sigma. So we only claim a discovery if there's at least a 5 sigma discovery. So in CMS we saw that, and then we say, well, we also have still the other experiment. There is Atlas. So CMS had 5 sigma, so 1 in a million, and Atlas had exactly at the same mass, also at 125 GeV, also of a chance less than a million, that this was a statistical fluctuation. So then we have enough evidence to say, like, yes, we have it. Rolf Hoyer said we have it, and Joan Condella, the boss of CMS, put his thumbs up. Rolf Hoyer actually said we have it. He didn't say we have a Higgs boson, because we weren't sure yet it was the Higgs boson, but we had the feeling it was something. And then 1 year later, Peter Higgs and François Englert, they got the Nobel Prize. So the theorists who predicted it in 50 years before, in 1964, they got it through the discovery of the predicted fundamental particle by the Atlas and CMS experiments at CERN's Large Hadron Collider. So we didn't get the prize directly, and because that's not the way it works with Nobel Prizes, but we were recognized in the text of the prize for Higgs and Englert. So Higgs and Englert got like a million, and we, in the CMS experiment, we got a barbecue. So here you can see us above ground at the CMS experiment. So here's a poster of the CMS experiment to scale, and if you look very carefully, you can see me here holding a beer up with some of my friends from Belgium, where I was working at the time, and you can also see my 2,890 part of my 2,899 co-authors, because the discovery paper had 2,900 authors of them, but I was happy to be one of them. So that was great, and it also concluded the standard model. So at the time we had a bunch of quarks, we had a bunch of leptons, we had a bunch of neutrinos, we had a bunch of force particles, but we didn't understand, or we didn't know for sure how particles got mass, and the Higgs boson was long predicted to provide a mechanism to generate the masses of particles. So this was really the final piece of the puzzle that was missing. But of course, as Fokke and Sukke say, you know, it's all very impressive, dear colleagues, but actually, does your observation also work in theory? So it's nice that we observed it, but does it work in theory? So what does the theory look like? Now, this is the formula of the standard model. So here everything is written out, all the interactions between the particles, so the interactions of the, for example, the W bosons and the Higgs bosons with the quarks and with the leptons. And what does this describe? Well, it looks a bit like a hieroglyph, right? But it actually describes the interactions between matter particles, so let's say the building blocks of matter, and the force particles. And we like to do this often with Feynman diagrams, which looks like a very simplistic drawings, but actually they have mathematical meaning. But they're also very useful to have a feeling for how our interactions take place. And for example, what you can say is like, okay, we have, for example, a fermion or a quark coming in, and it interacts, it is charged, and it interacts with a photon for the electromagnetic force with the other particles, and they repel each other. So that's the way it works, that matter particles interact with a certain strength via force-carrying particles. Now, and Higgs actually predicted the masses of this force-carrying particles, and later they also said that matter particles might get their masses in the same way. So, so what did Higgs actually write? So we saw a very difficult equation before of the standard model. Actually, the paper that Higgs wrote, for which he got the Nobel Prize later, was not even 2 pages. It was actually just 1.5 pages. And as you can see, the mathematics in it was actually quite minimal. It was really very basic, but it explained why particles have mass, and that's why it was so important and why it led to the Nobel Prize. So what did he predict? The prediction was that the potential energy of a certain field doesn't go just with a quadratic term, but it has this Mexican hat kind of shape. Some people also like to call it a wine bottle shape. My more fancy colleague, she likes to call it a champagne bottle shape. But anyway, so you have a quadratic term for the potential energy and to the 4th term for the potential energy. And it means that the potential energy is not minimal in the middle, but it is lower at a higher value. So it means that you have, it's energetically favorable to have a Higgs field everywhere. That was his prediction. Okay, and that's what we're still trying to test. And the way you can see it, and it's not very intuitive, but an analogy I like is to say that the Higgs field is everywhere, and it's basically like, we are basically like goldfish in a fishbowl with water. The water is everywhere. We don't really know it, right? So, I mean, yeah, there's water everywhere. There's also Higgs field here everywhere. We don't really notice it. But the water makes us go slower, and especially the heavy fish, they go slower in the water. The small little fish, they go faster in the water. So the friction of the water causes the more massive particles to go slower, and the smaller fishes to go faster. And also, if you are this fish and you want to discover this water, you have to find the drops of water. And those are the Higgs bosons. Okay, so our Higgs field is basically the water that the fish lives in, and the Higgs bosons are the water drops that are created out of it. And we have to discover those water drops in order to prove that this water exists. Alright? Don't take it too literally, but it's an analogy. But this was the explanation why an interaction of the Higgs with particles gives mass to the particles. So the way you can see it is that in these diagrams that we just saw, that a Higgs particle interacts or produces two force-carrying particles. And if we can see that, this might give us an indication that actually those particles have the mass and acquire this mass through the Higgs mechanism. So basically, in that way, we have to find that water. So how we did it is, as I just showed you, we looked for the Higgs to 2 Z boson. So a Z boson is basically a heavy photon And indeed, we can see there that the Higgs gives mass to these Z bosons. We can also see that the Higgs decays to photons, so also the interaction to these bosons can be explained by the Higgs field. And here we have a plot of a Higgs to WW, so also the W bosons get their mass through the Higgs mechanism. You don't have to remember these plots, but the bottom line here is the Higgs field gives the masses to all the vector bosons as far as we know, and in the way that Brout-Englert and Higgs predicted in 1964. But originally it was not known if the force particles got their masses like that, or also the matter particles. So we also had to check that, like, do the building blocks of matter, do they also get their interaction from the Higgs particle? Okay, do they also interact with the omnipresent Higgs water? So we looked, for example, at the Higgs to B particles. These B particles, they fly a bit longer than other ones, but they only fly like 1 millimeter. So in our haystack, we look for needles that are displaced by 1 millimeter, then flying 40 meters through our detector, and 1 billion times per second. So we have to write computer algorithms. That's actually what my students do, to actually find these tiny displacements in this mess of tracks. And we also then have a lot of backgrounds, as you can see here, in gray and yellow and green and blue. And we then have to find this little red excess here. At least that was what I was trying to do when I was in CMS. This was all the data of 2011 and 2012. And we barely saw the Higgs interacting with B particles. We also tried to look for a Higgs interaction with tau particles. So again, here in blue you see all the backgrounds. And in red is the tiny little bit of signal that we are looking for. So we really have to do a lot of effort to get this backgrounds, this signal out of the backgrounds. And these events are very messy. Of course, we don't take pictures of the events, but if you visualize them, they look like this. And you can see a lot of tracks coming out of the interaction that we have to reconstruct all the time. But the bottom line was, indeed, the force carriers, the W and the Z, they get their mass from the Higgs, and it seems that also the top and the bottom and the tau get their masses from the Higgs. And this is the plot I want you to remember tonight. If people ever ask you, why does the Higgs give the mass to the particles? Well, here you can see the mass of each of the particle and the interaction the particle has with the Higgs. And you can see that the top quark, which has a mass of 170 times 170 GeV, so the mass of 170 protons is together in one single quark. And this interacts indeed the strongest with the Higgs particle. The W and the Z are slightly lighter, they have a slightly lower mass, so they also interact less with the Higgs boson. And the B and the tau particle, they also interact less with the Higgs boson. And you can see it's proportional. Suddenly, I never thought of this before, but well, I'm being recorded, so maybe I shouldn't make bad jokes. But this reminds me, for the younger people, this reminds me of the fuck around and find out graph, right? Because if you F more, you find out more, right? So it's very proportional. So it's linearly proportional, so it really shows you the more massive the particle is, the more interaction it has. And that's what we've proven, and that's why we really believe now that this is the Higgs particle. And we've shown it for the matter particles, so for the building blocks of matter, but also for the force carriers. But we keep working. We're not yet happy because we think like, well, maybe we find something new, and that's what one of my students did at the UvA, Marko Stamenkovic. So he looked at the interaction of the Higgs boson with charm quarks. So if you look here, over here, there's nothing. And we said, like, we want to see also if the Higgs actually interacts with charm quarks. So we were the first to measure it. So this is the publication, and it's now 10 years later, as it was in Nature, again on Higgs Dependence Day, but then 2022. And we were the first one to put this point on the plot. It has a sizable uncertainty, but you can also see that this one is on the straight line. So we were very proud of that. Now, of course, on high school, you learned about the periodic table of elements. You know, you were sitting in the chemistry courses and staring at this thing like, you know, what should I think about that? Yeah, there's some structure in it, but it's not so appealing. We have our own periodic table, and it starts like this. So here we have the up and the down quark, and the up and the down quark are the building blocks of the protons and the neutrons. And we have the electron, which is also charged. And these are all the particles on planet Earth. You know, I've now been a physicist for like 20 years. I'm still amazed all the time that everything on Earth, your chair, my pointer, my glass of water, because I need some water, everything is just made of these three particles. Up and down quarks in the nucleus and electrons surrounding it. And that's it. And that's what we can make everything on planet Earth from. But turns out in our collision experiments, we find of each of these, we find three copies. So from the up we found the charm in the top. From the down we found the strange and the bottom copies. And from the electrons we found the muon and the taus. But that's it. Okay, so here we have this messy periodic system, up to 118 at least. But we see three copies of each. We have 4 by 3 particles, also 3 neutrinos. And we have 4 Higgs-bosons, and we have 1 Higgs-boson. And that's it. Okay, so, but again, yeah, the fact that you have 3 by 4 here, that makes us a bit like maybe there's something even deeper behind it, that we can even find something more fundamental. And so we have 3 copies of building blocks, 4 force carriers, and 1 Higgs field. And one thing that I think, like in the year, you know, when you learn at high school about, let's say something, you know, something that you think like, yeah, I could have also discovered it if I was at that time. I don't know. We're gonna, you know, that apples fall down. Newton. I think I could have been Newton if I would have lived at that time. Yeah, now it's much more difficult. I think in the year 2100, when our students see this plot, so here you have the particles ordered according to generation, so electron, muon, tau, up, charm, top, down, strange, bottom, and here you have the mass. If the students in the year 2100 see this plot and they say like, yeah, of course, there's a straight line through it, because, fill in your favorite theory, then that would be a nice explanation. Currently, we know that there's 3 copies of everything. We're all the time scratching our head like, why do we have 3 copies of everything? Not more, not less. And why are they also so nicely aligned in a pattern? And why does it seem to be like the lightest one are 100 times lighter than the medium heavy ones, and then again a factor 100 to the heaviest one? So there seems to be some pattern there. We don't know yet what it is, but it would be really nice if somebody comes up with it, and maybe it all makes sense then. Okay? And yeah, of course you saw I was wearing my t-shirt, so this equation here, actually you can write it much simpler. It might fit on a mug or even on a t-shirt, and this is actually the Lagrangian as we have it. So this explains the interactions between force carriers, this explains the interaction between force carriers and particles, this explains the Higgs interactions, and this explains this funny Mexican head shape. So actually we know a lot. We know that there's 4 times 3 quarks and leptons. We know that these particles have charge. I didn't tell you yet, but they have charge 0. Okay, fine. 1, that's also fine. But they also have 1/3 and 2/3. That's a bit funny, but it's really the case. We have 4 force carriers, and then we also have the Higgs interaction, which gives mass to all the particles. However, there's a lot of questions that we don't know. So I already mentioned a few times, why are there 3 copies? But also, what are neutrinos? Neutrinos are a bit funny. They have very small mass, but not 0. And they might be their own antiparticles. We're going to find out in the coming years. But this is also something that's puzzling us because it's not really described by the standard model. We would like to know, is there dark matter? What is the dark matter? Where did the antimatter go? Why are we on planet Earth in matter, and why aren't there equal amounts of antimatter in the universe? How is actually gravity supposed to be included? Because there's no gravity actually on this mug. And is there maybe a deeper grand unifying theory? And can we maybe answer some of the cosmological questions? So, for the next part, let me go a bit to the cosmology, because the Higgs might also be related to that. So, a very nice experiment that was very important for cosmology was this horn by Penzias and Wilson. This was in New Jersey, and they were supposed to look at listen to satellites, but well, there were actually already better apparatus at the time, and they were playing around with it because they had to do something, and then they found that there was noise all the time coming from everywhere. So they were trying to figure out what was going on. At some point they found pigeons in there, so they thought, okay, there's some pigeon poo. If we clean this, it will all be fine, all the noise will be gone. Or if we don't aim it at New York, maybe also the noise will be gone, but the noise was always there. And it turned out there was this cosmic microwave background, which is a bit more than 3 Kelvin, and it's just surrounding everything, everywhere. So there's a radiation coming from everywhere, and if you look at it, it looks like this. It looks quite flat and homogeneous, and it seems to indicate that that there was, for example, a Big Bang. And if you analyze all of this, then you get the standard model of, like we have the standard model of particle physics, they have the standard model of cosmology, which tells you that there's a Big Bang, this universe then inflated, it's then expanding in an accelerated way due to dark energy. There seems to be some extra gravity due to dark matter, and there's also somehow no antimatter. So this story works very well, and it can describe a lot of data. However, we don't really know what the Big Bang was. We don't understand what really inflation is. Dark energy, we also don't have a proper theory for it. Dark matter, okay, we're quite sure that it exists, but we still don't have really evidence for it. And the antimatter is also something to scratch our head. So we have something that works, but we don't really have a proper explanation why. And one thing that we hope is maybe that there's a link with the Higgs boson, because if we have our potential, we now have our theory from Higgs and Angler that tells us that this ball rolled down the Mexican head potential. But the mechanism behind it, like you have in superconductors also in the University of Twente, we don't really understand it. There might be actually a reason that it's linked to the Higgs, because this baryogenesis, as they call it, it might be due to bubbles forming, just in a way like water boils. So you have bubbling boils of water. We might have bubbling boiling bubbles of Higgs field in the early universe. And in that way, these things might be related. So how can we study this? Well, we know that this potential is like this, but if we go back to this picture with the interaction, so how can we learn about this quadratic term and this quartic term? You might think like, okay, this is just a formula. But actually, if you go deeper into the equation, you can actually see that this formula, that it's related to the fact that 3 Higgses interact with each other. So the fact that you see here a phi to the 4th, it leads to the fact that 3 Higgses can interact with each other. Or in another way, that a Higgs can decay to 2 Higgses. And this goes with a probability related to lambda. So this formula, where there's a lambda and a phi to the 4th, you can study it by looking for the process where 1 Higgs boson decays to 2 Higgs bosons via a probability lambda. And how do we do that? So we actually look for this process where you have 1 proton and 1 proton via quantum loops of top quarks producing Higgs bosons which decay to 2 Higgs bosons, and actually 2 students from NIKHEF and the University of Twente, Ellie and Osama, they are trying to see the first glimpses of this process. And actually, Ellie at the moment, she is in a meeting where she thinks that she will see the first 1 sigma evidence. Well, 1 sigma evidence, we learned that it's not really statistical significant, but we are really thinking that we see the first glimpse of 1 sigma of Higgs boson decaying to 2 Higgs bosons decaying to 2 B quarks and 2 photons. There she's trying to get the result approved now, and maybe in a few weeks it will be public. So don't put the YouTube video out yet in a month now. But, so that's what we try to do, and that's also what's happening in Twente. So the theory we have at the moment is described as this mug. So this is basically the Maxwell equations. We know it since the 19th and 20th century. This is the Higgs boson interaction with the force carriers. We discovered it in 2012. This is the Higgs boson interactions with the matter particles. It took a few years more, like 5 years ago we were really sure about it. But this last part of the mark, so the V, the potential here, that's really the last thing that we really want to check, because we're actually not really sure that this potential is the way it was described with this very simple formula with a phi squared and a phi to the 4th. So how are we going to do it? So if you look here at the amount of collisions that we produce at the LHC and the amount of data that we collect at the LHC, so we're now over here. You can see that we are now at 500 something. Doesn't matter what this inverse femtobarn unit is. We're now at 500 something, but we hope to collect in the end something like 4,000 of something. So we think our data set will still grow by a factor of 10, so we can study everything in more detail. So in the first run 1 in 2012, we discovered the Higgs boson. In run 2, we saw the interaction with the building blocks of matter. Now we are trying to study the interaction with lighter particles, for example muons. But the coming years, we're really going to learn about this self-interaction and the Higgs potential. Now, how do we do that? We actually, of course, we don't just do data analysis and making nice theories. We really have to build detectors. So here you can see one of these detectors filled with millions of channels of semiconductor strips. So these strips are actually like 10 micron large, but then you have a detector which is this big, so you have millions of readout channels of semiconductors in order to precisely reconstruct them. So this was built in Amsterdam, and you can see here also our technicians installing them, of course, with very high precision to be sure that we keep this 10 micron accuracy. Here you can see something I worked on myself. You can see from the masks, this was during the COVID time, but of course work still had to be done. I think we had to keep distance, but okay, for this picture it was like, okay, let's make a nice group picture together. And here you can see one of the detectors that had to be replaced, a new small wheel. It's only 9 meters, that's why we call it small, because the other ones are even bigger. That had to be replaced, and we managed to do that in 2022. And here you can also see me when I was in Germany together with a technician from NIKHEF and a student from NIKHEF. We were standing here, we looked a bit like Swiss cheesemakers. But this is actually a particle, one of the particle detectors in Atlas. And again, we align these with a precision of 10 microns in order to be sure that we can really measure these particles very precisely. So at Amsterdam we work at NIKHEF. So this was actually a picture from the time before the renovation, so I had to use some computer rendering, but now actually we have the building is renovated. And NIKHEF is very nice because it's a bit like CERN. It's a central research institute linking all the universities, and we're also the link to CERN. So there's not just students, but also engineers, technicians, and researchers, and we're at Amsterdam Science Park. So at NIKHEF, for example, we built these detectors and also the infrastructure. For example, you need cooling, you need electronics, you need cables, whatever you need here, of course, also has to be built. and nothing you can buy in the supermarket. We have theorists working on making a better mug, and we have a lot of students working on the data analysis. And of course, we like to also collaborate with Twente because magnets are important for the accelerator and also for making a good detector where we need a strong magnet. And actually, one of the magnets that we have in the Atlas detector was built in Twente. Now, what are we going to discover next? As the saying goes, predicting is difficult, especially when it concerns the future. But if you ask me what would be really your favorite discovery, I would say, well, you know, maybe there's a dark Higgs. Maybe the Higgs talks to the dark side, because you know the Higgs gives mass to other particles, and we know that dark matter has mass. So, well, it doesn't need a very big insight to think like maybe the dark matter particles get mass from the Higgs interaction. So if you look, for example, a diagram that you could draw, you could say, well, I collide standard model particles and maybe I produce a Higgs, and then the Higgs decays to invisible particles. So that's something that we are looking for and something that would be a really nice discovery because we discovered the Higgs-boson, so it might also be really nice if we could solve the riddle of dark matter. So how do we do that? It's actually annoying to search for something that's invisible, right? Because you cannot see that, but you can do a bit like, I don't know, playing billiards with semi-invisible balls, because if you would collide billiard balls with each other and some of them are invisible, you could still reconstruct from the visible balls what happens to the invisible balls. So if you, for example, produce a Higgs boson that decays to invisible particles, going like this, from basically Newtonian mechanics, you could see that if you have a visible particle here, maybe there's invisible particles on the other side. So we see such events, but there's also events we expect from other processes, so it still requires a lot of data analysis to be really sure about this. So this is maybe a bit busy plot, but if you look here at the dark matter mass, you can see here the experiments that are underground in Gran Sasso. So some of our colleagues also work in Italy under the Gran Sasso mountains. They put a liquid xenon jar in there of like thousands of tons of liquid xenon in order to see if there's dark matter particles. They typically probe the parameter space over here, and we typically probe the parameter space over here. So we probe the low masses and they probe the high masses, and we also have some overlap. So it might be that they see a signal at some point under the Italian mountains, and maybe we see something on the ground in Geneva, and maybe we can learn something about dark matter there. But we don't have conclusive evidence yet. We do see some hints. One of them that I like is sometimes we look for 2 Higgs bosons. It's of course very important for this self-interaction. And if you look here at 1000 GeV, you can see that we have an excess of 3 sigma. Okay, so it seems to be like a chance of 1 in a 100 or 1000 that there is an excess of 2 Higgses. We also see Higgses with a probability of 3 sigma that might decay to electrons and muons. It's a bit asymmetric. We also see an excess of 2 or 3 sigma of charged Higgses. And we also see Higgses at a very low mass, like 95 GeV, with again 3 sigma. But as you learned today, we need 5 sigma, and we need 1 in a million. I actually made it into the newspaper one time. So this was the Volkskrant, where Tijn van Kanthout was still writing for the Volkskrant at the time. Nowadays he works in our communication department. And he interviewed me here, and I said I was very excited. I was not the only one. Even Fabiola Giannotti, the Director General of CERN, she said that a bit of excitement is allowed. And what we were seeing at the time was again a bump, and it was even in the newspaper, so it was very nice. But you know, it was 3 or 4 sigma, so we were almost ready to be very happy. But we required 5 sigma, and in the end, that data went away. So we have to wait a bit longer. So we either wait longer, we collect more data, or maybe we build a new detector, new accelerator. Sorry. So the last 10 minutes, I will say a bit about the new accelerator that we're currently designing.
So here you can see from the Jura Mountains. I also used to ski here sometimes. So here's the Jura Mountains. If you look down, you can see the LHC like this. So here's the Lake of Geneva. Here's the city of Geneva. So the LHC goes like this. There's the pre-accelerator and another pre-accelerator. And the accelerator some people are proposing now is the FCC, the Future Circular Collider. And it passes by the Jura Mountains, it goes under the Lake of Geneva, then it goes behind the Pre-Alps, so this is part of the Alps, and then it goes all the way over there to France, where there's Annecy. You might have gone camping there on your vacation, and then goes back to CERN again. So instead of this 27 kilometers, this would be 91 kilometers. And as we learned before, if the radius is like 3 or 4 times as big, we can reach collision energies of 3 or 4 times more. So we like to have bigger magnets and bigger radius. So this could help us a lot. So in Twente, the EMS group is involved in it. So I'm also part of the EMS group. So EMS stands for Energy, Materials and Systems. So they, for example, work on particle accelerators, also on nuclear fusion, like ITER, and industrial applications like windmills, waste sorting, and those kind of things. And actually also in gravitational wave detectors. I think you should have another Studium Generale about the thing that they're currently trying to make in Limburg on the Einstein telescope. It's very exciting, and yeah, some of my colleagues that you might recognize, they're also working on this Einstein telescope over here in order to have mirrors that are even better cooled and less vibrant. But we also work on this future accelerators. If you follow the courses on Twente, you can also follow my course, Introduction to High Energy Physics. You can hear some of the same jokes. I might be repeating them, but I even have also other jokes. I had my exams a few weeks ago, and I was reading the answers of the students, and actually, like, I think there were like 5 students who were actually repeating some of my jokes in their answers to my exams. So that was nice. But we now have to build a new accelerator. So we are discussing what should we do. Should we collide leptons? Should we collide hadrons? Should we collide them in a straight line? Should we collide them in a circle? And where should we do it? Should we do it in Europe? Should we do it in Asia? Or should we do it in the US? So it's a very difficult discussion. It also involves time, it involves money, it involves sustainability, global politics nowadays. So it's very complicated. One of the proposals that's on the table is a 30-kilometer accelerator in Japan. So you can see an electron line of a bit more than 10 kilometers. You can see a positron line of a bit more than 10 kilometers. And then they just are accelerated in a straight line, so without magnets. And in that way, you can produce very cleanly Higgs-bosons if you collide electrons and protons. Because as you can see over here, in an electron-positron collision, it's very clean because you have particles, antiparticles, they annihilate each other and nothing else is remaining. So you can just see, for example, here is a muon and here is a muon. They come from a Z-boson, and here you can probably see a jet of B quarks and a jet of B quarks. So I can already see by eye that this was probably a Higgs boson being produced in this collision. So it's very clean, and that's why people like it. The electron is very nice because it's a point particle, but its disadvantage is it has a low mass, so we can in principle not reach as high collision energies as we could do with a proton. So for the protons, we are thinking of this accelerator at CERN. So here you can see the view from above. So Jura, Alps, towards Annecy, ring of 91 kilometers. And there we can accelerate protons because in a ring you cannot accelerate these light particles like electrons, but protons does work, and then you can reach very high energies. So that one has the advantage that you have a large mass, but the disadvantage is, what's the disadvantage of colliding protons?
They're not point particles.
Yeah, they're not point particles. Very good.
Because they're made of 3 quarks. So if you collide a bag of quarks and gluons, and you collide it on another bag of quarks and gluons, you first create a big mass, but you also don't use all the energy, because this one has maybe 1/3 of the energy, and if you collide it on another one with 1/3 of the energy, you have much less in the collision energy than what you would have had with point particles. So, what would be the best of 2 worlds? Which particle has both a large mass and being a point particle? Anybody wants to guess?
So maybe electron, but like the third one?
Yeah, the second one even is good enough.
Oh, the second.
The muon, yeah, very good. So, the muon, it's a point particle, like the electron, but it's the heavier cousin of the electron. It has a big mass. So it's very nice, because you have a point particle where you use all the energy of the collision, and you have a high mass, so you can also accelerate it in a circle. So yes, we are happy. A point particle and a big mass. So it's clean, like E plus E minus, and it's energetic, like proton-proton. And we would also need a smaller infrastructure. We don't need a 90-kilometer ring, maybe we can do it in a 27-kilometer ring that we already have at LHC. So what is the catch? What is the problem with the muon? It's not stable. Yes, very good. It's not stable. How long does it live?
Fraction of a second.
It's 2 microseconds. It's in the name because it's 2 mu-s. Sorry, another lame joke. So it's like a millionth of a second. So producing muons is not so difficult. You shoot protons on the target. You make pions. The pions decay. You have muons, but then time starts ticking. Now you have only 2 microseconds. How can you solve this? Muon lifetime is 2 microseconds. We made a whole drawing of how we can do this. So we first make protons, we shoot the protons on the target, we produce pions decay to make muons, and then we have 2 microseconds to accelerate in a 27-kilometer ring. How can we get around this fact that we have only 2 microseconds?
Accelerating them faster is not an option, right?
Yes, that is what we have to do. Een echte muon collider fysicus kan niet zonder gamma. Maybe this joke is too old to get. Gamma, the gamma factor from Einstein tells you about time delay. If you go very fast, your clocks go slower. So if you go very close to the speed of light, you will live longer. So if we make a muon, if we increase its energy such that it's like 100 times heavier than it usually is, then it will also live 100,000 times longer. So it might actually live. If we accelerate into 5 TeV, it might actually live 1/10 of a second. And then we are almost happy. So, so if we accelerate them, we manage to we produce just many of them, and then some of them of course will decay, but if we accelerate them fast enough, we can actually make them live longer, and then we collide them both. So thanks to Einstein, if we use relativity to let time go a bit faster, we can produce them, cool them, and accelerate them and collide them in 100 milliseconds. 1/10 of a second. It might be enough to go around this 30-kilometer ring with the speed of light. But we need to develop this technology. This technology is not yet ready. But in Twente, people are working on parts of this chain in order to make these magnets, to make this maybe work in the future. So what CERN's future will be, we don't know yet. We now have this 27-kilometer ring here, but maybe we make a new straight one. Maybe we make a big one, but maybe we can have a muon collider ring. Who knows? So at the moment, actually from 2024 to 2026, we have the European Strategy of Particle Physics. At NIKHEF, I'm also involved in this, but there's also many other countries. All the member states of CERN and also the non-member states have their opinion. And we are discussing now this in 2 months in Venice. In June, we will have a big gathering of all the particle physicists to define this European strategy to see what we should do next. So that will be very interesting because it might define for decades what is to come. And then we hope that maybe we learn if this is everything, or if there's maybe something deeper than this, or if there's other particles than this. For the moment, we don't know, but we think we should still search, and we still have good indications that something else should exist. And I really hope that, well, I just had coffee after dinner with Peter. Peter liked long coffee, but I had an espresso. At CERN, of course, everybody drinks espresso. And then maybe our big equation of the standard model will also become an even more compact equation to describe everything, the theory of everything that would fit on the espresso cup of CERN. So thank you for your attention. I hope you enjoyed it.
Thank you. Tristan, thank you very, very much for your fascinating talk. You discussed a lot of very exciting physics. The future as well, it's dancing a little bit because there's lots of information. We have about 20 minutes for questions. So I have a few on my notes here, but I want to give you the first opportunity. I will get the mic, just a second. Go ahead.
Yeah.
You showed the standard model, the position of the Higgs particle in it. He is ranked in the scalar bosons, but there's only one scalar boson, that's the Higgs boson. The question is, isn't there a whole family of Higgs bosons? Because I read somewhere Steven Weinberg was discussing with Frank Wilczek about this family. There would be actions or Higglets. So, do you work on this?
Is the Higgs boson alone, or is there a family?
No, so yeah, when I was a student, one of my favorite books was from Hawking, and at the time, Hawking and also at Hoofd, and when I was a student in theory, we really believed that SUSY would be found, supersymmetry would be found at the LHC, and in supersymmetry you have multiple Higgs bosons. So instead of this one, because you have this one doublet, you would have two, and it would predict 5 Higgs bosons. And that's why also I showed that you know, we might have some indications that maybe there is something here. So what I would have liked, for example, is that this particle at 1 TeV, so 1000 GeV, that this, when it decays to two Higgs bosons, this might be a heavier Higgs boson. And they are predicted in supersymmetry. And also those charged Higgs bosons, they are also predicted in supersymmetry. So we believe they might exist, but for the moment we don't have any statistically significant evidence for that. For your axions, that would also be a nice solution to the dark matter problem, and it's a very elegant solution because it would solve 2 problems at the same time, and that's also why it's called the axion, because axion is also a cleaning material, so it cleans up 2 problems. And also at CERN we do an experiment, so we actually take one of those LHC magnets, we point it at the sun, because we think that maybe in the strong magnetic fields of the sun, these axions are produced, they fly to the Earth, and in the strong magnetic field of the LHC they get converted into light again. So also that we are doing, but also there we don't have any evidence yet. But yeah, they are 2 of our typical things that we hope for, like heavy Higgs bosons would be a really nice candidate for something beyond the standard model.
Okay, this action protocol, could you say a little bit more about it? Is it very heavy or very...
So yeah, that is the difficult thing, because it can have a lot of mass. It can have a large range of masses,
Yes.
and it can have a large range of couplings.
Okay.
So it's very difficult to find them.
Mhm.
So with the LHC magnet, we look at them, but it covers a small range. For example, Daisy in Hamburg is also very active on it. They have some new experiments where they're also going to search for it. But it's you have to probe a lot of
parameters in order to be sure. But it would be a very, Bilczek said it in the 70s when he predicted it, that he thought it would be found in 1 or 2 years. So, because it was obvious, nice theory, but
Yeah.
In practice might be difficult.
Yeah. Okay, thank you.
Thanks for the lecture. My question is, in terms of, you mentioned sustainability, what are the main bottlenecks that stop these experiments from being developed further on? Is it finance? Is it law? Is it policy? Is it how you dispose the parts that didn't work out, that are not needed? What are the main concerns, so to say, to bridge the theoretical things needed and practically implementing it?
Good, thanks.
You mean the new accelerator?
For example, or the current one.
So, I mean, for the new accelerator, you know, there's so many variables in there. There's, there's money, there's sustainability. It also depends what people find important themselves. So, I am personally a bit worried that the 91-kilometer tunnel is considered a bit expensive.
What type of how much will it cost?
So such a tunnel, I think such a tunnel will be, so we now actually have the numbers because in this European strategy update, the tunnel will be typically like 7 billion euros. And then
They need a few magnets, I think.
and then the accelerator on top of it, that would be like 10 billion extra. So you're talking about 17 billion. There's also a Chinese proposal. Chinese proposal is very similar. Actually, China also wants to have one of also like 100 kilometer. Yeah, in China it's much cheaper, of course, because also the labor for the tunnel will be much cheaper, so they can believe they can do it for less money.
Okay. And related to your question, if you have the Large Hadron Collider working, how much energy does it use?
Yeah, so the energy consumption is not so much on the beam, but it's a lot on the cooling.
Yeah, exactly.
And this thing, the LHC was of course made in different times when we didn't care so much about sustainability. So these magnets, they are cooled at minus 271 degrees Celsius. So that's very cool, and that costs a lot of energy. So we hope that if we have better magnet technology, for example niobium 3 tin, that we cannot just reach stronger magnetic fields, but we can also have the settings that is less critical for the temperature. So we can maybe run it at higher temperature, which would also reduce the electricity consumption. Of course, electricity consumption, not just for sustainability, but also for the financial part, is important.
Yeah.
For the sustainability, you also have to think of the concrete. I mean, in 2050, probably all the electricity is green. Anyway, I mean, LHC runs on French nuclear power plants, so you could say that already, that the electricity is green. But of course, the concrete is actually quite sizable part of it, so that is also something to keep in mind.
Yeah, but when it's fully operational, how many energy is it using? How many?
Yeah, typically the number is like half of the city of Geneva.
Okay. Yeah. Well, that's a clear answer.
Hi, yeah, so you mentioned sustainability. Of course, this is a very similar question to the first one. If you're proposing the new mu1 accelerator ring, as you can see on the map, and if it's going to be around the same size as the already existing one, would it not be more sustainable to repurpose the original one?
Yes, very good. No, indeed, that is. I mean, now they have been drawn on purpose next to it. Like, okay, it could be any size, but yeah, one of the really big advantages is if we would just put it in the tunnel. So there's actually plans to reuse this LHC tunnel for the, not for the collider, but for the accelerator, because with the muon experiment you need both a collider ring and, you need an accelerator ring and a smaller collider ring, but you could reuse this as the accelerator ring, and you can even reuse one of the pre-accelerators. So yes, that's definitely an advantage.
Thank you.
Mm-hmm.
And actually also in the US, because here we have a 27-kilometer ring in Europe, but the US is also very enthusiastic about the mu collider, and they already have a 10-kilometer tevatron where the top quark was discovered. So also the Americans might consider reusing their tunnel.
Yeah. Okay. Right.
You mentioned the issue before, in the beginning of your presentation, the issue of recording data from the collisions. With the number and the frequency of the collisions, it's just like mind blowing to me how so like could you talk more about how you manage to analyze the data before it gets recorded, with the frequency of the collisions?
So, yeah, there's two parts in it, because one is what we call the trigger, and one is really the data analysis. So the trigger really makes like an instantaneous decision, like should we record it or not. But it also uses a subset of the information of the detector. So for example, you just use a very coarse information of the colorimeter energy or the muon detector, just to know like is it more than a certain threshold. And then when you've written them to tape, then we say, okay, now I have that is actually written to tape. When I say tape, it's really tape, because tape is better for long-term storage. Then we have our algorithms, and we take our time to analyze them properly, and then we have more time, because this instantaneous trigger just uses less information to do that.
Okay. Is there a relation between gravity and the Higgs field, or is this a silly question?
No, that's not a silly question. The development said that there's so much potential energy in here that the universe should be curved like a football, because of all the energy that's contained in the Higgs field. Yeah, I mean there's mass, there's gravity. We also think the Higgs could be related to inflation. Think like this could be related to baryogenesis, like the way it's bubbling. But this inflation, it might also be related to the way that this ball rolls down the potential. So there's many things there to believe that the Higgs could solve, but we don't know it yet.
Okay. And perhaps a related question, the Higgs-boson itself has a mass.
Mm-hmm.
Does it produce its own mass? How does it work?
Yeah, so that's from this, am I going in the wrong direction again? Yeah. So that is from this interaction. So that's basically this.
Okay.
This interaction is the interaction with itself, and this also gives a mass term related to this lambda.
Okay.
So yes.
Yeah.
That lambda, is that related to the lambda expansion of the universe?
No, that's capital lambda.
Okay.
Oh, it's not.
Two different lambdas. Go ahead.
I had another question about the boson itself, the Higgs boson itself. So, since it's a particle, does it also exhibit any wavelength properties, or no?
So I think the lifetime is like 10 to the minus 22 seconds. What we actually currently do, people are asking good questions, but also difficult questions. But what we actually do, so wavelength, I would have to think about what we do study nowadays in order to access its width. So width is related to, it's quantum mechanically related to lifetime, because like in Heisenberg's uncertainty, you have delta p delta x coded h bar. So the better you know the location, the worse you know the momentum. Something similar you have that if some particle that lives shorter has a larger width, and we measure this width from the interference with itself. So that is maybe related to your wavelength question, but the lifetime is 10 to the minus 22 seconds. But how it relates to the wavelength, I would have to think.
Mm-hmm.
But in principle, everything with energy has a wavelength, right? It's a bit out of
If it has
Just a second, and we can all hear you, yeah?
But then, if it has a wavelength, so it also has like this wave particle relatively, but is it closer to its property to an electron, where it has like probabilistic distribution, or is it closer to a photon, where it has like a wave with like kind of like discrete energy?
Good question.
good question. It also lives very short, so I don't know what you can do with it in this 10 to the minus 22 seconds. I mean, nowadays we do look at quantum entanglement of top quarks, but I don't know if we can do something with quantum entanglement of Higgs-bosons.
Just go back to the Higgs boson and the Higgs field. You said the field is like the water and the boson is like the drops forming the water. Could you say a bit more about the difference between the boson and the field, the Higgs boson and the Higgs field?
Yeah, because we normally say that the particle is the excitation of the field. So if you think of the electron, it's like an excitation of the electron field, and Higgs boson is an excitation of the Higgs field. So the Higgs field is non-zero everywhere, but if you have a particle, it's enough energy to excite it out of this water.
Yeah, yeah. And did I understand it correctly that your mass at the moment is completely arranged by this Higgs field?
Yeah, so
Is that
I hope that we can find a lower interaction strength so I can lose weight very easily.
I was thinking more on the statistical side. So why is the threshold for the statistical significance 5 sigma, so 1 in a million? Considering the collisions per second, this does not seem like a really big number. And do we expect this threshold to change once we have new discoveries?
So yeah, there's a few things to that. So I mean, first of all, I could give the arrogant answer by saying that we use 5 sigma, like social and medical sciences often usually only use 2 sigma. Yeah. So you know, when they test medication, for example, they have to have some threshold, and they often use 2 sigma. Whereas if you do a lot of measurements, this is difficult. Of course, they don't have the luxury like us that they can do 1 billion experiments per second, right? They have a limited sample size. So, okay, so that is the easy answer. Then, you know, there's frequentist statistics and Bayesian statistics. With Bayesian, you also include your prior. Your prior belief that something is true. With the Higgs boson, it was predicted since 1964, and we knew what it was doing, and so we were like, okay, it follows exactly the theory like it was 50 years ago. You know, it behaves exactly like that. It quacks like a duck. It walks like a duck. It must be a duck, right? But nowadays, we also have, for example, in the LHCb experiment where I was working before, they also have discrepancies with the prediction. But they don't really have a good theory behind it, and there's not really a good prediction why they would see such a signals. So in that case, you get something like extraordinary claims require extraordinary evidence. You say like, okay, maybe then in that case 5 sigma is not enough, and we actually want to have more evidence before we conclude anything. Also because we do a lot of measurements. So if we these were the Higgs measurements, but we do searches for all kind of beyond the standard model particles. If we do 1,000 searches, of course one of them will be an outlier, one of 1,000, right? So in that way, that's why we also usually include the Luke-Alver effect. It's like suppose you would do if you would do medical studies, like are these pills curing something? And you say, oh, but maybe the red pills are curing something, or the blue pills are curing something, or the green pills are curing something. Then if you repeat this sample size, you will also always find somewhere outliers. So that you also have to correct for. So I agree with you that 5 sigma might not be sufficient, but it depends a little bit still on the case. But so it's not like when we see 5 that we immediately call the newspapers and we will say like, now we have evidence, because we also have to convince ourselves. But at some point, the signal can also just be so nice that you're like, when they discovered the gravitational waves in 2016, 17, 100 years before it was predicted by Einstein, and people thought it would be too difficult to see, it would be so difficult to get out of the detector, and when we saw that signal, well, not we, but my colleagues from the gravitational waves, it was so nice, and before it, you would also think maybe we need 10 sigma significance, but it looked so perfect exactly how it was predicted, and it was 5 sigma, and it was like, yeah, this is just very convincing. So there's also a psychological element to it.
Thank you.
Yes?
Yeah, so in 2013 and 2019 we went to CERN, to the open days, or open weekend, I'm not sure what it was called back then. Does it ever happen again?
So I can. That's maybe not good because I'm now going to show you a schedule which is outdated. 3 at the time it was supposed to be between 2025 and 2027. It has been moved a little bit in the meantime because there were some hiccups. Building the new detector was difficult. Of course, there was also COVID here, so that also shifted everything. So LS3 long shutdown 3. It's gonna happen between 2027 and 2030. Okay? Or sorry, 2026 and 2030. I have the schedule always written on my whiteboard because it changes all the time. I cannot even Google it, so I always write on my whiteboard what the schedule is. I think it's from next year summer for 4 years long. Yeah, from 2026 to 2030. So then the LHC is off for 4 years. So then it will be probably easier to visit CERN because then the accelerator is off, so you can go down. Because other years, like now, you would have to go in winter because for the electricity prices, we're always off in winter, but we run the rest of the year. So actually now the LHC is starting up, but from medium 2026 to 2030, there's probably going to be open days because it's going to be off for 4 years.
Okay.
Will also be a lot of upgrade work for Atlas actually.
And what does open days mean? You can enter.
Yeah, probably that they organize something that a lot of people can go down the detectors to visit.
Detector.
Yeah.
Okay, cool.
Yeah, I think it's a bigger deal than you make it sound like. I think it was really interesting, and if it happens in open days, then everyone that thinks this was interesting, you should really go because it was very cool.
Okay.
Everything was impressive there.
Thank you.
Maybe one more question just to refresh my own memory. Once I was there, we heard that the protons are accelerated for about a day before they actually collided into each other at the colliders or detectors. Is that true?
Yeah.
And if so, I think it was also that it wasn't necessarily accelerating them to a higher speed. It was more so to give them more energy.
Yeah.
So how does that work exactly? Because if I take EMC squared, where's the energy then?
I mean, so first you have a bottle of hydrogen. I mean, this bottle of hydrogen, it's 10 to the 23 order of 10 to the 23 atoms. So you can run the LHC for the rest of your life. So then you strip them. You strip the electrons from the protons. Then you accelerate the protons straight, you throw them to the booster, you throw them to the proton cyclotron, you throw them to the synchroproton cyclotron, you put them in the LHC, and then you have an energy of like 450 GeV. So then you have to ramp them up to like 6,000 something GeV, so a factor of 10. So that ramping up, then it's already in the LHC, and then you basically give them every time a kick they go around. And you have to strengthen the magnets, I guess, and then you ramp up the energy until it's at 6.5 T. Now it's 6.8, and then you keep shooting them onto each other. But every bag of protons is like 10 to the 11 protons. So you shoot them, and slowly you finish them. But you have so many protons, and protons are stable that this amount of protons you have slowly diminishes. And currently it's optimal to dump them after half a day. So after half a day you say like, okay, now the beam gets less bright, let's throw them out and put new particles in because then we have a brighter beam again. But it's just, I mean, in principle you could run it for a few days, but then of course slowly you get less protons in the accelerator, so it's better than to dump them and to put new protons in there.
but protons are stable, so there's no reason to.
But where does the energy come from? Because I think they aren't really accelerated much more.
No, but they also don't lose much.
Right.
That's the advantage of protons versus electrons, because this gamma factor from from Einstein, this energy loss, they call it synchrotron radiation, goes with the gamma to the 4. But an electron has low mass, right? It's half an MeV. So when you accelerate it a lot, it will also lose a lot of energy. But a proton is already heavy by itself, so it doesn't lose a lot of energy from turning it around. So you just have to keep it in a circle with your magnets. So that is why you like to keep those protons in the storage ring, and the electrons, because they're different. And then for the muons, you have to be, you have to throw a new beam in every second.
Yes. Thank you. We have to round off, unfortunately, but the suggestion of going to CERN from excursion is a very good one. We will keep it in mind. Tristan, thank you very, very much. This lecture was titled, Is There Life After the Higgs-boson? Yes, there is. We can conclude that's a very clear conclusion. And I want to end with the CERN gang sign. It's the right hand, but please all do it. So, the CERN gang sign. Yeah, you can all do it. Right hand. Yeah. Okay, very cool. Tristan, thank you very much. Big hands for.